Thank you, and thank you to the AIG for the opportunity to present on this. A obligatory first comment, as I think everyone has done, I'm not a data scientist, I'm a geoscientist who's starting to play with some of these techniques and concepts. And a lot of the stuff I'm going to be talking about is related to the same project that Dave has just talked about in terms of the Northwest Mineral Province. So there'll be some similar slides, but hopefully I'll be able to present with a more geological context of why GSQ is going down this route and how we're working to that, analysing our data, and then looking to develop new programs. So I'm really talking about regional applications of machine learning and how we're looking at that in that space. I'm going to start talking a bit about the GSQ and its purpose there. I'm going to get on to the Northwest Mineral Province data-driven mineral exploration project. I'm going to pick a couple of those reports, a couple of those sections that some that Dave did talk about, some that Dave didn't talk about in that, around mineral potential modelling, some classification problems, and also some anomaly detection in that. I'm going to have a bit of comments about some limitations and issues in regional applications of machine learning. There's been some examples before about people talking about how much data they've got. And we've got voluminous data, but over a large area we have very sparse data in a lot of our regional applications. Talk a bit about some future ideas of what GSQ is looking into machine learning, and then I'll do a bit of a focus on a broader project that GSQ is undertaking, looking at our Geoscience data modernisation program, which is really looking at uplifting the availability of our data. GSQ is a custodian of a lot of exploration data in Queensland, and hopefully by doing that work we will enable others to do that machine learning by having that data availability. So to go way back, the GSQ was formed 151 years ago after the discovery of gold in Gympie. This is Richard Daintree, who was our first government geologist, and he was tasked with defining the prospectivity of the state. And they realised quite early on that was a big job, and so they brought on another Alpin as a second geologist who had the southern half of the state. Daintree had the northern half of the state, and they were pretty good going on from there. But really, the work in the early GSQ was about really defining those economic locations, those gold fields, those coal seams, and doing the actual discovery work, mapping the fields, mapping the areas, and really doing the discovery. This is one of the first maps that Daintree did of up in the Cape River goldfields, and this is a more recent map of that. And you can see similar features exist across both those maps there as well. So the GSQ has the same purpose. It's about growing the prospectivity and the economic potential of Queensland. But the role has changed over that 150 years from being the discoverers to being those that enable the exploration and the discovery. That's something we're doing through geological mapping. So there's some early geological maps and then some more recent geological maps there. Through geophysics, I mainly did this to put up this image because I just love this is one of the first geophysical aerial geology surveys that was done across the northern half of Australia. I believe this was the current chief government geologist at the time. I don't see Tony Knight getting up there and flying thousands of kilometres in a plane like that. And this is one of our new geophysical data sets. And a lot of other work, a lot of more geophysics work, a lot more of geochemical work. But really, another role that's really grown the GSQ is we've become the custodian of reports and exploration data, both from stuff done by ourselves, GA, the academic community, and also exploration. And that role as a data custodian is becoming of much greater importance over time. And I think we've gone from the role where I think even when I started, GSQ was nearly a reluctant data custodian. We had data, we had reports, we held them, to really it's driving the way that we do things now. It's really that data-driven exploration is really driving everything we're doing at the GSQ at the moment. And we're really, hopefully, taking on that role of the data custodian and hopefully providing value back to the industry in that space. So a lot of this work is around the Northwest Mineral Province. 75% of Queensland base metal mineral resources. I've got silver, lead, zinc and copper, gold, but if you can name a mineralisation style, you can probably find it in the Mount Isa area. There's hundreds of years of histories of exploration and discovery in the area. You've got Mount Isa mines, you've got Ernest Henry, Cannington, Century, large mines in that area. But if you put on the geological map of the area and then you overlay it with the known deposits in the area, it looks like a rather scattergun plot until you bring on the outcrop line. where you can see that pretty well 99% of those occurrences occur where the rocks are outcropping. If we skip forward and we look at our depth of basement, this is an earlier depth of basement, we have had some updates to it recently. There's a lot of area around that outcrop that's in very explorable regions that hasn't had the discovery rate that we would expect looking at the outcropping areas. So really we've got to drive that exploration undercover, and that's harder. And so it's how we can help industry with that driving exploration undercover. And this is a slide that Rick created a while ago, and I think it's similar to a lot of the other slides we've seen before. The industry is drilling more, they're spending more money on exploration, but over time we've had less discoveries, and those discoveries are getting deeper over time. So we've got a decline in discovery and increasing discovery depth, but at the same time we've had a wealth of new research, discovery work done by GSQ, GA, industry, academia, lots of different programs, CRC works. So there's a gap. There's a gap between all that new work, all that new data, all that new discoveries, all that new research, and exploration success in that space. And we think that is really about taking that data and creating meaningful insights from that data. So to reiterate that another way, we found the easy to find deposits, and I don't mean to pick on anyone by saying what we've done so far has been easy to find, but we're moving on to harder to find styles of deposits. Past exploration data has resulted in good discoveries, and there's been lots of good work in the area, but we've reached the point where we have a knowledge transfer gap. So all that new research, all that new activity hasn't created new discoveries. So exploration costs are going up, discovery rates are going down, the value of good data and good insights is increasing. So as part of that, the Queensland Government formed the Northwest Mineral Province Task Force, and we proposed a project with Cyro Minerals and Data61 to look at what current machine learning strength and abilities could be used on our open file data, improve our own internal skills in understanding the needs of ML, both in a data set and skills requirement, and to showcase, I guess, what could be done with completely open file, open data in the Queensland area. And work was really focused on the eastern succession of the Northwest Mineral Province. So the first thing we did, and Dave talked about this as well, was looking at the Quambi 3D model. So this is a model that we did in 2013. Back then we built it as a 3D geological model in GoCAD with geophysical inversions. We populated that with evidential properties, so it was a knowledge-driven approach based on the mineral systems team at the GSQ's understanding of what drives mineralisation, or what we believe is related to mineralisation in that area. And then we did a 3D weights of evidence approach against our known deposits in the area to target, to assess the relationship of those evidential criteria against mineralisation, but then also create a mineral potential map there. So that was our weights of evidence mineral potential map of that area. And that is log scale. It does look quite pretty at that point, but it is quite a stretched log scale, I would say. So one of the first steps we did with this work with Data61 is we looked at taking that area where we had already curated that data, cleansed that data, brought that data into one system, and running it through a logistical regression machine learning technique. So if I bring it to a similar scale, this is the results of our weights of evidence approach in 2013. So you can see it captures the known mineralisation quite well, but you can see one of those features that was in the machine learning was structural, was related to the fault network. And so you can see the fault network stick up quite nice in there. A lot of false positives created by the largest faults we have mapped in that area. We step forward now to look at the logistical regression. We have far less dependence on that structural complexity. You can see it's capturing the same results, the same training data. So you can see Ernest Henry down at the bottom there for scale. It's getting those where we would assume would be higher potential along that structural complexity related to those marine intrusions of the Williams batholith in the area. So it's performed quite well, and Dave had the curve showed how well it had captured our known training data. One of the limitations again was in this area there were 15 training sites of known mineralisation in this area, and so a lot of the machine learning struggled with having such a low set of training data available. So coming forward, the next one we did was a geological classifying tool. So this is using random forest, using all the surface and geophysical covariates we could, so a lot of ASTA, DEM, gravity, grads, and maybe radiometric. And this is focused primarily on our simplified surface geology. So taking that surface geology over the whole northwest and bring it down into about 30 morphological units. So we ran that through a couple of different methods through the random forest. First one we used 1% of each class or each mapped cell to train the model and then saw how it went. And then we went through a couple of steps, and I'll go through that. So the first one we did captured the geology quite well. So this is our surface geology that we map, the geoscopy map. This is the result of the random forest in our exercise in there, using 1% of every one of those classes as training data for that, which is a lot of training data to drive that. The probability here is really the confidence, so you can see it's quite confident down here where the NWMP batholith is. And the difference is where you've got areas that have been reclassified or haven't been reclassified. The reclassified areas are in blue, and the red areas are where it hasn't been reclassified. So, in a bit more of a stretch, we use 415 of those sample points as our training data, and then ran through again. Much less, it does get the broad structures, it does get the broad geology, it does miss a lot of the area. It's quite confident again down where the NMWP batholith is because it has a good understanding of what that unit is. But at a first pass, it does give you a good understanding of how you could use that to train up the geological map of that area. These are just some local areas now. So this is an area where we trained it using 10% of the mapped geology in the area and then fed that back into the random forest classifier. And you can see an area where we had a fair amount of outcrop that performed fairly well in a first pass. But we had less outcrop, it started to struggle a fair amount. So you can see it captures the broad geology in the area, but really starts to struggle once you get into areas that has no understanding about that here. As a bit of a trial, they also ran it through the solar geology. This obviously was never going to work great because your ASTA, once you get into your undercover areas, your ASTA, your radiometrics falls apart, your DEM probably doesn't have much relevance to your geology anymore, and you really rely on just your gravity and your magnetics to give you any confidence. So you can start off with 2 points per class and everything is granite, which is, good potential there. Even as you get up to about 200 points per class, you can see it captures some of the broad structures, but really it's not an appropriate technique for this. And I think that's one of the lessons that we learn from these things is you can try things out and see how they work quite quickly and easily with a machine learning technique. Probably was never going to be an effective technique used in random forest on solar geology using ASTA and radiometrics. So that was also related to some of the work that Dave talked about as well, classifying the outcropping granites. I like the classifying outcrop granites because as a geophysicist, I like this granite, not granite, and probably not granite classification of rocks. So there were 5 different granitic suites, and then not granite was the 6th class trained there. So there's the input model there. So we had our surface geology comes out, the random forest prediction, the Williams-Narracube batholith gets quite close in a lot of that there, so you can see it's quite confident in that area. There's not a lot of change there. A lot of the difference occurs in a lot of the other suites. And we can see the reason for that is coming into the amount of data points we had there. So in our not granite, covered 76, 77% of the training data, followed by the Williams-Narracube, which had 12% of training data, so it knew the Williams-Narracube quite well, whereas some of the other granite suites that had far less data to drive that, so it wasn't as good as predicting that, those suites of granite, so it was less confident or less able to predict some of these smaller Caldoon or yeah, there we are. That's sweet. Thank you. And this is something else that I think Dave pointed out as well. Looking at our current surface geology mapping and the model prediction. So this area is an area of shallow alluvium over the top of what is probably the Williams Anomaly granite batholith run underneath it. So the data density wasn't enough to really drive this this little shallow inlet of alluvium in there. But again, you can look at that. If you understand why the model's doing that, then you can look at if you need to update the model or whether this is a fine result. I think a lot of the times we look at machine learning, we look at the final result as being the important thing, but it's actually the learnings and the steps that we go through that iterative process are the most important things we gain from that. Coming up with a map with reds and blues and stuff like that is interesting, but what we're really looking for is the learnings or understanding about how related data is in that. So the anomaly detection again was a nice, I think quite interesting feature Dave did. Dave talked about it quite well. As we go through, I think what you find here is a lot of these anomalies sit on the edges of units, and that's where we expect anomalies to sit, along the edges of units. But something else we can look at here is the mean anomalous distance to the unit, how anomalous the unit is on average. You can understand maybe some of these units down there that are quite high in this, maybe we need to reclassify. Maybe there's a bimodal distribution of those units that have, again, this is using only magnets and gravity to drive this. Maybe you've got a unit that has some mafics as well as some felsic units in there that's been classed as a single unit. And so maybe this can drive how you might want to break up the units a bit more. Or if there are areas that are systematically along the edges of boundaries that your model has, if those boundaries are precise or if you need to look at affecting those boundaries. So that report has been published in QDX reports, and all that data is available in QDX data. The link down here is for that. And again, I'd like to acknowledge the work that Cyro Minerals and Data61 did in producing that report. Just on a bit about limitations in regional machine learning in this space, most data sets on a regional scale are very sparsely distributed, and they have a very non-uniform distribution. There's a lot of geochemistry, drilling, all sorts of data around mine sites, around exploration permits, and then once you step out into greenfield terrains, you have gravity and magnetics. And if you're undercover, that's basically all you've got in one of those spaces. So you do have a limited set of those regionally continuous data sets outside of your gravity and magnetics, some regional EM at times. You have a very strong sampling bias. Again, so you have lower data density and variety in greenfield terrain where we want to be exploring. And the prospectivity modelling is limited by our train and validation and test data, as well as the amount of positive samples we can use to train the classifier in that space. And I guess one of the other limitations that I wanted to bring out there is the importance of those spatial relationships. As a geoscientist, you understand that this unit here, one cell across, is going to be very well spatially related to that unit. But a lot of the classifiers will put a unit that doesn't occur within 150 kilometres of that in that area. Now that's not wrong. It's just saying that the classifier looks at that data and sees it as most like a unit that doesn't occur in that area. What you need to look back there is, again, look back at the data, understand what is about that area that is causing a lithological unit that you know will not appear in that area to exist, to be created by the model in that. And that's where that iterative process of understanding what the results are telling you and going back to look at these. So I guess, and this is future GeoScience, my view of what we should be doing, because no one's signed off on this yet. So I think we'll be augmenting our existing geological mapping processes using machine learning techniques. Back in before I started GSQ, GSQ used to send many FTEs out for half a year, field mapping, map sheets, over and over again for years and years and years and years. And you can see the Huttons and the Donchats and the Withnells on every map in Queensland if you've got it. That's not something we're going to be doing into the future. We don't have the man hours, we don't have the budgets to do that sort of mapping. So what we will be doing is doing targeting mapping based on areas that we have need to refocus or where the model may disagree with our current mapping. So we'll be using machine learning to help drive area selection for those, and as well as understanding where new data is needed to get better predictions. And I'm sorry, Brett, we're never going to fill that hole in the mag ranges in Queensland, unless someone else wants to fly it, maybe Sol could commit to that. That'd be great. So as well as using machine learning within GSQ to support our workflows, we also understand that we collect and curate a lot of the data, and we want to enable others to do that. So I'm going to talk a bit about open and fair data, and then I'll talk a bit about the Geoscience data modernisation program. So open data is a concept that I think we've talked about for a long time. Open data should be freely to use, modify, and share for any purpose. But we're moving beyond open data, and we're talking about a new concept called fair data. So we want to make sure, as a survey, and I think a lot of the surveys are starting to talk about fair data now, that our data is not just open, but it's findable, it's accessible, it's interoperable, and it's reusable. And so when we want the data to be discovered by machines as well as humans to enable this new style of machine learning and data accessibility. We want the data to be accessible, and that doesn't mean that all data is open. We have a lot of confidential data, but we should have the data open when it's available to be open, or as open as possible if we can. Data should be interoperable, so we need metadata and standards around that data, and it should be reusable. So you need to have that understanding of the provenance of the data, so machines can read it and use it for other purposes moving forward. This is a chart from Forbes, and basically it's what data scientists spend their time doing. And you can see the biggest chunk of this time here is in the cleansing and organising and collecting the data sets. It's taking about 80% of the time of that machine learning. And I think in geoscience it's the same. It's collecting the data, it's finding the data, cleaning the data and getting to a state you can actually use it takes the majority of the time. And so I apologise to anyone that is interested and excited about data. Oh no, it's the next slide, so this one's alright. So you'll understand that there's will be some heart attacks in the ring when we get there. Currently we think that the availability and discovery of the data is not optimal, and we're looking to go to a state where we want to have the systems, the people, the technology and the processes optimised to enable better discovery of data. This is the slide I was going to scare you about. This is a photo of some of our data. I will promise you that this is not how we store all of our data, but this is some of the data stored at our exploration data centre. It's tapes from seismic surveys, it's boxes of reports, it's legacy geophysical data. Most of this is stored online as well. But what's happened here is that the value we've taken to collect all this data is now lost. There is no value left in this data because you can't find it, you can't access it, you can't use it. So if you can't find and access and use the data, there is no value left in that data. So part of the Geoscience Data Modernisation Program is basically an uplift of how we manage, curate and deal with our data to drive towards a state we call data-driven exploration. So there's 4 pillars in this. We're talking about our data input first. So that's about our reporting requirements on how we ingest data into our systems, looking at confidentiality of data in terms of how long data needs to be held confidential before it can be made open file, and having templates for reporting data so data can get into standard formats. Data curation, this is around our data lake, so this is where we're going to store a lot of our data and cataloguing a lot of our data, and I'm going to come to the data lake in a second. Value add, this might be GSQ, it might be industry, it might be academia, that's looking at intelligence or building insights on that data to enable new discoveries from that data. And also industry enablement to work on that cross-collaboration of skills in that space. So they're really the pillars of that, and that's really what's driving a lot of the work at GSQ at the moment. So when I talk about data lake, we have a pilot at the moment. We're moving a lot of our data up into Amazon Web Services. So we've got about 60 terabytes currently in Amazon Web Services in S3 storage in a data store, a data lake. So we're storing every piece of data as an object. And then we have a catalogue that catalogues all our physical and digital objects. So that might be physical objects like our core store or our tapes, or those data boxes that you saw at our exploration data centre. That catalogue is really essential to everything. It drives the discovery of our data. We have data access, and that's human or it's cloud. Human or computer machine, and cloud data access into that data lake, data catalogue. On top of that, we have data processing that might be looking at our old PDF reports, running through TextRact on those to get some understanding about more metadata to add to those, to attribute those reports better, and cleansing and curating that through that data. Visualization tools, so we can visualize things in 3D or in graph databases or spatially or in whichever way we want. Analytics, again, to find insights within our data. And then machine learning on top of that to identify patterns and insights in the data. That might be something that we run the machine learning, that might be something we have abilities for APIs to plug in to run machine learning on data. But hopefully the idea is that the data is available for those that want to use it in that way. So the catalogue really underpins what's going to work in this space. So the really important things are we're looking at building standardized data schemas so we can describe the data as well. We want controlled vocabularies and ontologies, so what I call something, we know what that means, we can understand that. So we're doing a lot of work at the moment in building those data catalogs, building those ontologies around the data to describe the data. We're going to have consistent identifiers so you can understand where that data exists and the provenance of the data as it goes through. And then link data so we can understand relationships between our data sets, reports, and objects. So we have a pilot of our Geoscience data Modernisation program out. Currently there's about 800 seismic surveys, geochemistry database across the whole state, about 12 terabytes available data, and that has a CCAN portal on top of that with an Amazon Web Services data lake. And that is a live link there, and we're starting to add more and more data into that. The next thing that will go into there will be our company reports, which we're going to mark to make sure that I'm saying the right thing. So we're going to take all the company reports from QDEX and bring them into the data lake. The data will still be on QDEX reports, as you know there. You'll be able to access it through a different way to find that data and hopefully drive new discovery of the data. Yep, cool. So I guess the mission statement of the GDMP is optimising the geoscience data ecosystem to unlock the full value of data to enable exploration success. And I guess my take-home messages on the Northwest Queensland work we've been doing, it showcased the regional application of machine learning and the hidden potentials of our open file data. Machine learning, I think I'm going over things that people have said over and over again already today. It's an iterative process of exploration and discovery with data. It's not like you do your model, you press the do machine learning button, and you get a result that has reds and blues and go and drill reds. But it's about discovering through your data. I think a lot of the machine learning is not about the answers. You get to ask the right questions and understanding the outcomes of those questions. And that comes back to garbage in, garbage out. You can put anything into machine learning and press the machine learning button and get a result, but is it meaningful and what does it understand? And I guess, again, machine learning is just another tool to aid in the exploration tool belt. It's not a panacea to solve all of our exploration problems.